Seisenberger from the University of Swansea on the computational content of the minimal bad sequence argument.
Thank you very much. So, at first, I would like to thank the organizers for inviting me to this wonderful place here and give the possibility to study here. Then I want to say my talk will be very informal. It's on the board, and it's not technical. And please interrupt if some definition is missing. And third, I was asked to, when I was asking, can I give my talk at the end that I have done the research, then people said, no, that's not the intention. So we want you to say what you want to do, and then we'll see what comes. So that's why to the title of the talk I come only towards the end, so I put the title here. I want to start with giving an overview of about the general research area where I am. That's program extraction from proof. And in one sentence to lay out the agenda is establish program extraction from proofs. From proofs as a competitive method for program development and verification. So what is program extraction from proofs? So if you have a formal proof, then by some method we can automatically generate a program. And the method we're using is modified realizability. You might know from proof theory. So we are using modified realizability because actually we extract terms, and not only natural numbers. We get our realizers are term and not numbers. So from a proof, we extract a program automatically, and we also get a soundness proof for free, plus soundness proof. So I give two static examples for that. So the first is a verified quotient remainder program. So if we look at the following formula, so for all two natural numbers a and b, so b not 0, we can extract quotient and remainder fulfilling that a is b times q plus r, and r is the remainder is less than b. So from the formula we can already read off the type of our program. So what we expect a program getting as input ab and output two natural numbers, a pair of natural numbers, so quotient remainder with the desired behavior. And how to prove that? So it's we do it by induction on a. So if a is the number 0, then we put both quotient and remainder also to 0, and to make this equation true. And if we have from induction hypothesis quotient and remainder which fulfill that, then to find nu, q and r for a plus 1. How to do that? Yes, it depends on, so if from induction hypothesis we have quotient remainder with this desired property, then there are two possibilities. Either from here we still can increase the remainder by 1, then we take that one, or we already would reach the B, then we have to increase the Q. So there are two possibilities. The first one is we take the old Q and R plus 1, and the other possibility is we increase the Q and set the remainder to 0. So a simple proof. Now how about the program? Now normally I would give a demo. So because programs start to make sense if you have appropriate tool support, so I would give a demo in the theorem proof of Minlog, where we have implemented all these. And this time I thought I have only half an hour, I have no time for that. So I simply put the result on a slide. So that would be a term fulfilling that. So it takes in the lambda term, so two numbers. We have done induction, that corresponds to recursion. The base case, we take a quotient minus 0, 0. And in the step case, we have a case distinction, so an if statement. And we have the two cases. Once we take, so P3, that one is simply we get from the induction hypothesis. So it's a pair, so P for pair. So for the quotient remainder fulfilling A equals something. So, and here, that one, so one sees here maybe. So as we take the old Q and increase the R by 1, so successor, or we increase the Q and set R to 0. That is the result. And then one can run it. So for instance, so the extracted term with the numbers 20 and 3, and the result is a pair of numbers 6 and 2. So 20 is 3 times 6 times plus 2 remainder. And also, just to demonstrate, that's in Minlog still. So the program runs via term rewriting. And we can also automatically export to a scheme. And here the pair left and right would, here you find a lot of cars and couriers for the projections of the pair. So that is just, I think it's a bit small, you can't probably not see very well at the back. It's just that this automatic support really in a programming language is available. My second example is a bit more involved. So example 2. So extract a sub-solving algorithm. So, and to the end we have formalized a DPLL proof system for non-satisfiability. So Davis, Putnam, oh, I have forgotten now, the other two people who were involved in the creation of that. And the statement we are going to prove is for all valuations, gamma, so valuation, simply a set which is a valuation, a set of literals, and for all formulas in C and F, conjunctive normal form, formula, we have either that this formula is not satisfiable. That means there exists a derivation in the proof system, which I, for simplicity, have put on a slide. So this is an inductive definition that that essentially shows unsatisfiability. So if the left side is empty, then we have the satisfiability problem. But for the definition, we put here evaluation. And maybe to quickly go through these 5 rules, and then I continue here. So if that reads as a conjunction, so if we have a clause which is empty, then we are done, so refuted. If we have a clause which contains literal, then we need to make that literal true, so we can put it into the evaluation. Then here, the next two cases, if one of the clauses contains a literal, which is already in the valuation, then of course that is trivially true, so we can remove it. And here, if the opposite literal is there, then we can't make it true because the literal is in the valuation, so we can remove that one. And then we have a split rule that says, okay, if none of the others is applicable, then we simply choose a literal and make the literal true or the opposite literal true, and then we see how to continue. And of course, that is the expensive rule because that blows it up. So what are we proving? For all valuations, for all formulas, either we have such a refutation, or we can find a model which satisfies both. So the valuation and the formula. So this means actually for each clause in that formula we find one is a true literal. Okay, I don't go into this proof because that would be an own talk, and also the program to show would be a bit more involved. What I wanted to demonstrate that actually by doing a proof we can get a program, and the program is of course verified. And that has been formalized in Minlog by our PhD students, Andrew Lawrence, and he will present that in the forthcoming MFPS conference. So to proceed with the agenda, so I said that's the aim, and there are, to reach that, there are actually 4 steps. The first is the theory and appropriate tool support. The next one would be demonstrate advantages. The third one concerns the feasibility. And the fourth apply to new areas. So quickly go through that list. Is theory and tool support. Actually, there we are already quite good. So in the Minlog proof system, we can do proofs in arithmetic. We can use inductive definitions. We have co-induction available, and also classical reasoning. We can extract programs from classical proofs via both A-translation and dialectical interpretation. So that is already quite good. And the only thing what one would like also have would be the possibility to extract imperative programs, and maybe also to extract programs from second order proofs. That would be in the future. Then demonstrate advantages of this method would be, of course, the obvious advantages. The extracted programs are provably correct. What I here mean, demonstrate advantages over other methods to generate programs and verify them. And the other methods I typically call over the specify, implement, verify method. So here, normally what you do is you specify an algorithm, what you want to do, you program it, and then later you look at it, how to prove it correct. And in our method, you do the proof at first, and you get the program for free. And not only the program for free, also any data structures which are needed to do the program. For instance, in computable analysis, if you reason about exact real numbers, then you don't need to write, deal with streams, writing programs with streams. You simply do your definitions, which are co-inductive definitions, and the rest is for free. So Ulrich will talk in the next talk about that more. Then often one hears, yes, but normally I have already my algorithm. I know exactly how it looks like, or I want to program something and I want to have hands-on my algorithm. I want to optimize it. So and so that's covered in that part, feasibility. So the question is, how do we need to do the proof that this optimized algorithms come out for free? And that's actually possible. So for instance, in that example, we have done so apply the split rule only if absolutely necessary, and also the question with which literal to choose. You can build that into your proof and get it. So then feasibility also concerns apply to larger applications. For large applications, very important is to have a good modularization technique available. Otherwise, it can expand too much and you can't use it anymore. And then fine-tuning, I said already. And the last thing is you would like to, of course, to exploit classical proofs. I will get to that in a minute. And question, can classical proofs lead to efficient programs? And that's to be proven. Because classical proofs, as we know, are often quite short, concise, and we know them already, whilst maybe finding a direct constructive proof is more involved. Then apply to new areas and extract new algorithms. So very promising at the moment is computable analysis. Then we also have extracted so far normalization algorithm. We have done worked in constructive analysis, in infinitary combinatorics. One area where it could well imagine would be the extraction of security protocols, because there you always have some technique, and then to you extend it slightly, but you could maybe reuse the old proof and to cover the new thing. So far, with that general part of my talk, now, I said already, feasibility. Here, how about classical proofs? Can we deal with them? And here my third example. So given an infinite Boolean sequence, so f from nut to bool, find A an infinite constant subsequence, and B find a constant subsequence of a given length. So if my booleans are 0, 1, then and my given sequence is 0, 1, 1, 0, 1, 1, 1, 0. Then I could decide, for instance, choose the ones and so on, if they occur infinitely often to do that. So that's a bit of an informal presentation. normally I would need to write down, find a list of indices so that the sequence at those indices is constant, has the same value everywhere. Okay. So to prove it, and that I typically call that the infinite pigeonhole principle. So if you have finitely many holes and have infinitely many things to put in, then there must be at least one hole which has infinitely many pigeons in it. So proof. So B follows from A, that's clear. From A and A, I want to do a certain classical proof. So either my given sequence is constant true, constant 1, from a certain point on. Either there exists a k that for all a larger than k, f of I is 1. So the sequence looks like that one. And then maybe it becomes always 1. Then of course I simply take that subsequence. Or for all k, I always find an I which is larger than k, so that f of I is 0. So no matter how far I go out, I'm sure there will be a 0. So even if there are many ones, this condition says me that there is always a 0. And then, using a choice principle, dependent choice, for instance, here, I simply can take those zeros and can build a sequence of zeros only. So that's of course a classical proof. So I can't say whether the sequence really has always ones, unless it would be explicitly given. And question, can we extract a program for A and B? Obviously, we can program we can extract for the not for the first one, but for the second, which is a consequence of that. So we use that one to get a program for that, for any n. So I can approximate this infinite sequence. And how to do that? So program. So I take the proof, then which is classical, translate it into a constructive proof. And so using the method of A translation, which essentially is double negations plus the so-called Friedman trick, get the constructive proof, and then from that I can get my program. The problem still was we have the choice principle we have used in here, because if I do double negate a choice principle, then the translated one is not a choice principle anymore. So if I take dependent choice, do double negation, do the Friedman trick, so take the goal formula and replace all buttons with that, then this one has not the form of a choice principle anymore. So what I can do to still run the program is provide a realizer for that directly. Provide a program for that directly, put it in, and then extract and then run the program. So how can a realizer for that look? So that is, for that we would use a so-called bar recursion functional. So modified bar recursion that has been found. So it goes back to Spectre and has been modified by Ulrich and Paulo Oliva. And so just to give a definition of that one, so it takes two functionals, yt and s. So that s would, in our choice principle, that s would store is a finite list and would store already elements which I have computed. And I have to extend that to determine. So, and these two are two functionals, and the type depends on the form of the choice principle. So on the premises of the choice principle, or on the premise of the particular instance. So y, so s, then take this s, concatenate it with an infinite sequence, so that's finite, concatenate with an infinite sequence, lambda k, then here g. And inside that functional, now we put mbr again. But here applied, extended by one more element. And it's allowed to depend on s and k. So that is, of course, a complicated thing. Probably one more. A complicated thing. And to compute that value, we have to extend it. And we have to look further and further. Does it terminate? So it terminates because we have a model for it, the computable functionals. And we would use the principle of continuity. It tells us we only need to look at up finitely many values, and then bar induction would allow us to go back to the empty sequence. So just a short discussion of that one. There are two other functionals. The one is a functional by Berardi-Kokon-Becem, Berardi-Becem-Kokon, and the other one is the iterated product of selection function studied by Escado and Oliva. And Martin Escado, he will be here in 2 weeks, so maybe he's talking about that one. What we have done, we have actually taken the three functionals and have compared them, which one has the best performance. And I think the modified bar recursion, what I take, had only the second place. So to show that this has been done, oh, my talk is almost over, so I need 1 minute. I have a problem now. So I spent too much time on that one, obviously. So here, that's the extracted program for that example. And in the third line, it has the psi. That is where this functional will go in. And so now I have to talk actually about this one, because this I have done already. The next thing, what I wanted to talk about, is actually Hickman's lemma. So, and at least I want to write down the statement of it. So if A is a very quasi-order, then also the finite lists in A are very quasi-ordered. So what means very quasi-order? Means that there is no bad sequence, and a bad sequence is so there is no infinitely descending sequence and not infinitely many uncomparable elements. And to the proof of that is in 3 steps. So assume there is such a bad sequence. So, as I said, that means there can't exist a bad sequence. Then we can construct a minimal bad sequence. and get a contradiction. So a classical proof, we construct the minimal belt sequence, so step by step, and we need again a choice principle to get the full sequence, and we get in a third step the contradiction from that. And actually that proof I also have formalized some years ago already, but now whilst looking at these different functionals, I thought, okay, and learning from that, it might be worth to look at that proof again, make it more modular, extract to a lazy language, because that is important, and understand actually that program behind that proof. Also compare it with a direct proof of Hickman's lemma. And what would be the most interesting thing, that's the title of the talk, is instead of giving a realizer for dependent choice, give a realizer for this argument, which I have not now explained in detail directly. And once that is done, one could think of extending the program for Hickman's lemma, extending it to Kruskal theorem, a similar statement just about trees, or the extended Kruskal theorem, graph minor, and so on. These are extended Kruskal theorems, and graph minor there are only classical proofs known for that. And another extension would be beta quasi-orderings. So this minimal bit sequence argument has also a pendant for beta quasi-orderings, but that I'm not sure whether that has computational content or whether it's possible to extract computational content. So that's the end of my talk. So sorry that it was a bit rushed at the end and that I couldn't show the whole argument. That's what I intended originally to do. But I hope you have nevertheless, it could interest you for that program, getting programs from proof is an exciting thing.
Okay, well, we'll move straight on to the next talk, since time is up.